We usually imagine Earth as a perfect sphere, but unevenly distributed magma and rock cause gravity to pull with different strengths. Visualizing these fluctuations reveals a lumpy shape called the geoid. Here, seawater pools in strong gravity and sinks where the pull is weak. In 1948, Dutch geophysicist Felix Andries Venning was conducting a gravity survey from a ship when he discovered the most extreme gravitational dip on the planet. It sits south of India, in a region known as the Indian Ocean Geoid Low. This map of the anomaly reveals a deep purple circular depression covering 3 million square kilometers. In this specific region, the gravitational pull is so weak that the sea level sits 106 meters lower than the global average. For 75 years, this 106-meter drop in the ocean remained one of the most significant unexplained phenomena in geology, as it appeared to defy every conventional rule of plate tectonics. We have launched spacecrafts to the far reaches of the galaxy, yet we've never designed a probe capable of reaching the base of our planet's crust. Most of our direct knowledge of the Earth ends just 35 kilometers down. The cause of this massive gravity hole was hiding hundreds of kilometers below the ocean floor, a depth completely inaccessible to physical exploration. Earth kept this secret for decades because we lacked the specific tools required to see through the crust and map the deep mantle. In May 2023, researchers at the Indian Institute of Science, in collaboration with the GFC German Research Center, published the findings that resolved the anomaly. They used a method called seismic tomography. By tracking earthquake waves as they travel through the planet, researchers can generate a three-dimensional image of the Earth's interior, acting as a high-resolution ultrasound for the mantle. They processed this seismic data through supercomputers to simulate mantle convection, the incredibly slow movement where hot rock rises and cooler rock sinks due to changes in density. The team focused on a basic rule of physics. Gravity is a measurement of mass. A gravity low, like the one in the Indian Ocean, must be caused by a massive deficit of material deep underground. The computer simulations identified exactly where that mass was missing. They found that a vast volume of abnormally hot, low-density rock has replaced the cooler, heavier rock that should be sitting beneath the Indian Ocean. The researchers traced this hot rock back 20 million years to a massive collision. As the Indian tectonic plate drifted rapidly northward, it crushed an ancient body of water called the Tethys Ocean. The cold, dense floor of that ancient ocean didn't just vanish, it was pushed down, sinking deep into the Earth's interior. This sinking slab eventually hit the bottom of the mantle, crashing into the African superplume, a massive, dense region of hot rock sitting near the Earth's core. The force of that sinking slab squeezed the superplume, forcing plumes of hot, light magma to drift upward and eastward. This low-density material eventually parked itself directly beneath the modern Indian Ocean. Because this trapped rock is hotter and lighter than its surroundings, it has less mass. That lack of mass exerts a weaker gravitational pull on the surface, causing the ocean water above to drop by 106 meters. The mechanics of the Indian Ocean anomaly lie in an ocean that no longer exists. To understand why gravity is weak south of India today, we have to look at the wreckage of the Tethys. The Indian Ocean Geoid Low is effectively a geological ghost, the surface expression of ancient tectonic movements happening thousands of kilometers beneath our feet. It is a reminder that the seemingly solid Earth is a slow-motion, turbulent storm. The maps we use today are still being shaped by collisions that happened millions of years before humans existed.